So let's think about how we could establish that n log n is a lower bound for the, or anything at all is a tight lower bound for the complexity of sorting. So what we're going to do is we're going to focus on the concept of element comparisons. Okay, so our focus will be, in this lower bound argument, will be on comparisons. So a comparison is just an operation that looks like this. And you've thought about this a bit in the midterm. So it's something that says, you know, is AI, or is the element at index I in this array less than or equal to the element at index j? Okay. So now why would we think about comparisons? Well, so far we've seen comparisons as kind of the basic operation in all of our sorting algorithms. So there's a couple reasons. So far, all our sorting algorithms, right, focus on so far. All of our sorting algorithms have relied on comparisons. Right? Comparison is kind of the thing that it uses. So we can almost think of sorting algorithms, or at least comparison-based sorting algorithms, as a sequence of comparisons that lead us to an answer. So you can kind of reframe the problem of sorting as, how do I want to arrange my sequence of comparisons so that at the end, so that I have a small number of comparisons that need to be made, and at the end of my sequence of comparisons, I have identified how to sort the array, right? So let's just sort of abstractly think of sorting, at least comparison-based sorting, right? This turns out to be important. So sorting is abstractly a sequence of comparisons. Sequence of comparisons. So what we'd like to do is we'd like to reframe our algorithmic question into this kind of decision theoretic question of essentially, what's the shortest sequence of comparisons that we can come up with that guarantees an answer to the question. Okay, so our focus will be on thinking about how short we can make this sequence. Make the sequence short. Okay, because if I can identify a lower bound on the number of comparisons, and I can say it takes at least this many comparisons to sort an array, at least if I'm using comparisons, then that gives me a lower bound on the algorithmic complexity. Because if the algorithm is using comparisons, then it can't be any faster than the number of comparisons. Okay, so it makes the sequence short because then the number of comparisons, or maybe we could say the minimum number of comparisons, is a lower bound on algorithmic complexity. Okay, so now let's think about how we would do this. So this is an idea called an information theoretic approach, and I'll talk a little bit about what that means as I go through it. But if we think about sorting as a sequence of comparisons, what we could do is we could take an actual sorting algorithm that we know, and we could write down a decision tree that uses these comparisons. So we could say, let's take these comparisons and think about each two-element comparison as a decision, right? And so when I ask this question, is the element at index I less than or equal to the element at index j, I get a yes or a no answer. And I could think about building kind of a decision tree where I say, if I get a yes, then I go this way, I go down this branch of the decision tree. And if I get a no, then I go down this way. I go down this branch of the decision tree. And I could start thinking about how the properties of the decision tree that is induced by an algorithm affect the complexity of that algorithm. So I'm going to pause the video and write a partial decision tree for a sorting algorithm, and then we'll talk about what it means. And poof, there's the decision tree. So what are we looking at? Well, this is the decision tree that is induced by selection sort, when selection sort is applied to a 3-element array. So this is selection sort 3 elements array. So let me just write n equals 3. N equals 3. Okay, so how does this work? Remember how selection sort works, right? Selection sort says, first let's go find the smallest thing, put it in the front. Then let's go find the second smallest thing and put it in the second position. Okay, and by doing that on a 3-element array, that suffices to sort the array. So the first question it asks is here, and it asks essentially, is A the smallest thing in the array? Right? That's what it means to say, is A less than B? If the answer is yes, then it goes to check to see if A is less than C. If the answer to that is yes, then we go to the left here, and then we say, well, so now we've identified, so by the time we're here, we know that A is min. Right? That's what that yes means. So now if we know that A is the minimum, now we have to go make sure that B and C are in the correct order. And so now here we're gonna compare B and C. If B is less than C, then we say, the output of this algorithm should be ABC, right? The array is already sorted. And if C and B are out of order, then the output should be this one. Should be that A, C, B, right? So this is what happens if we identify that B is smaller than A. So let's back up on the tree a little bit and go over here. Now let's say that A turns out to not be the smallest. Well, if A is not the smallest, then we don't really care about A, so what we do is we move on to B and C. If we identify that B is less than C, what does this tell us? Well, this tells us that we already know now that B is smaller than A, and so now here, at this point, we know that B is the minimum element in the array. So now we put B at the front, and we just have to go figure out where A and C belong. So now this tells us that B is the minimum, and now we have to compare A, B, and C. So we're gonna or A and C. So we compare A and C. If A is smaller than C, then we return this. If A is larger than C, we return this. Okay. So now let's think about these two branches that I haven't explored yet. So far we've looked at this branch, and we've looked at this branch, but what about this one? So what if we're here and we identify that C is less than A? Well, what do we know at this point? We know that A is less than B, and so if C is less than A, that actually tells us that C is the smallest element in the array. So now if we go down here, what is the next decision? I mean, this decision tree is just written out as selection sort would perform the comparisons. But it turns out that in this branch, if we say no right here, we actually know how the array is sorted. Right? The algorithm has actually done enough work. It's done enough comparisons that if we were clever in looking at it, we could say, well, now we're done. Right? Because what do we know? We know that C is smaller than A. We know that A is smaller than B, and so this tells us that C goes in the front, and A goes in the second position, and B goes in the last position. But the problem is that selection sort asks another comparison. Okay? Selection sort says, well, I just have to verify that B is less than A. But it already compared B and A, right? It already knows a ranking between B and A. So there's only one possible output of this decision, which means it's a wasted decision. And we get exactly the same thing here, right? So these two, let's draw an arrow. These two are wasted comparisons. So this doesn't factor too much into our lower bound analysis, but it does give us a window into why selection sort is inefficient. Because selection sort, it just isn't optimized to perform a good number of comparisons. We could end up with a scenario like this where essentially selection sort is gonna ask a whole bunch of the same questions over and over again. And what you would actually find is as this decision tree gets deeper and deeper, that is, as the array here gets longer and longer, requiring more levels in the decision tree, you would find more and more waste, right? More and more repeated decisions that don't need to be repeated. But let's look at this decision tree and try to interpret it a little bit. So first, let's ask, how long is the longest execution path in this decision tree? Well, every execution path has three comparisons, right? And so what we see is, suppose we use selection sort to verify that the original array is sorted, then we've got a comparison here, we've got a comparison here, and we've got a comparison here. Right? So the longest decision path in this tree is 3 comparisons long. Okay, so longest decision path is 3 comparisons. So suppose I gave you a decision tree and I said, this decision tree is the comparison-based decision tree for some sorting algorithm, for some input length. And I said, now tell me how many comparisons this algorithm is going to make on that size input. You would be able to, without knowing anything about the algorithm, you would be able to look at the tree and say, well, let me just find the deepest decision path. Right? The longest decision path will be the worst thing that the algorithm could do on that input, on that size input. Okay, so in a more abstract, more general sense, what we can say is that the worst case complexity of an algorithm for sorting of a sorting algorithm is it has to be at least the height of its decision tree. Okay, so we know now that selection sort is always going to do 3 comparisons on its on a 3 input array, and we see that some of those comparisons are wasted. There's no way any sorting algorithm can do much better than that. But in a general sense, in an abstract sense, if I'm trying to optimize a sorting algorithm, what I'm trying to do is make it so that the decision tree associated with that sorting algorithm is always as short as possible. Right? So our goal in fast algorithms is short decision trees. Right? That's the connection that we need at this stage. Okay, so if our goal is to have short decision trees, and so notice we're abstracting away anything that has to do with swapping elements or storage or recursion or anything like that, and we're just thinking about lower bounds for the algorithms, right? And so we can always say that the height of a decision tree is a lower bound for the complexity of the algorithm. So now let's think about what it means to design short decision trees. So now we're barely asking an algorithm question anymore now. Now we're just asking something about how does information get processed by the algorithm, right? Rather than looking at details of algorithms and details of storage and swapping and comparisons, now we're just going to say, let's try to come up with some kind of argument that says, here's the best that we could imagine ever processing information, okay? So let's think about what the decision tree is doing. Okay, what is the actual purpose or function of the decision tree? We know that we want short trees because short trees mean that the decision paths are short, which means that the algorithms are fast. But what's the decision tree doing? So what is function or purpose of the decision tree? Right, where DT stands for the decision tree. So what a decision tree will do is I'll give it an array, and then the decision tree is trying to figure out which permutation of that array is sorted in correct order. Okay, so the decision tree takes array and then identifies the correct permutation of that array that is sorted. And so I'll say a specific permutation of the array. And we can go and we can look at our decision tree that we had earlier, and we can check that this is actually happening. Right? So if I give it an array, I'll give it that array. What it does is it performs a series of comparisons, right? A series of binary decisions. And then at the end of that, at the leaves of the decision tree, it returns it returns a permutation of the input array. And so you can actually check and make sure that all 6 permutations of our input array exist as leaves on the tree. Okay, so the number of leaves of the decision tree has to be at least the number of permutations of the input. Okay, so the leaves of the decision tree correspond to permutations of the input array. So these are the leaves of decision tree. And for the decision tree to be expressive enough to actually solve the problem, it has to have at least one leaf for every possible permutation. So we need at least one leaf per permutation of array, right? We need to make sure that every possible output, which corresponds to swapping elements of the array around or identifying a permutation of the array, every possible output can be reached by this sorting algorithm. Okay, so now what does this tell us? Well, this tells us that we need at least n factorial leaves. Okay, so where did n factorial come from? Well, n factorial is the number of permutations of n items. Right, so this tells us we need at least n factorial leaves in our decision tree. So let's just draw a cartoon of our decision tree. Right? We know that there needs to be at least n factorial down here. So the question is, what's the shortest decision tree that we can create that has n factorial leaves? And now notice that we're not even asking about sorting anymore. Now we're just asking about trees. We're just asking about the shape of trees, right? So we want to minimize the height of a tree, of a binary tree, right? Now I'm not even writing decision tree anymore. Now this is just a binary tree. It's a pure graph theoretic question now. Minimize the height of a binary tree with n factorial leaves. Okay. And this is now a question that we can apply some just basic discrete math tools to answer.